Born-Haber cycle. Usually in a Born-Haber cycle, it consists of enthalpy of formation, enthalpy of atomization, ionization energy, electron affinity, and lattice energy. Lattice energy means energy released when 1 mole of solid ionic compound formed from its gaseous ion. So from gaseous ion as the reactant to form 1 mole of solid ionic compound. This is the product. Solid ionic compound is the product. Reactants, gaseous ions. Lattice energy is the energy released when 1 mole of solid ionic compound formed from its gaseous ions. For example, the reactant gaseous ions are Na plus in gas form plus Cl minus ion in gaseous form, and 1 mole ionic compound, solid ionic compound. Here 1 mole, and the state must be in solid. So that's what we call delta H lattice, energy release when 1 mole of solid ionic compound formed from its gaseous ion. So delta H lattice is equal to negative because energy release. So exothermic, negative sign, 771 kilojoule per mole, because here the product 1 mole of solid. Lattice energy can be also defined as energy required to completely separate 1 mole of a solid ionic compound into gaseous ion. If you reverse this equation, if the solid ionic compound as the reactant and the gaseous ions as the product, it is energy required to completely separate 1 mole of solid ionic compounds into gaseous ion. So here at the front, the solid ionic compound as the reactant and gaseous ions as the product. So the delta H lattice is equal to positive energy required. If you want to break this NaCl into the ions gases, energy is required, so it is endothermic reaction. If you reverse this equation, the sign will be opposite sign. So here negative sign, here this is positive signs. The value are the same because you're using the same equation. You just reverse it, so you just change the sign in front. Magnitude of lattice energy depends on 2 factors, ionic charge and ionic radius. Lattice energy of magnesium oxide is bigger than magnesium fluoride due to electrostatic force of attraction between Mg2 plus and O minus. So the electrostatic force between Mg2 plus and O minus is stronger than the electrostatic force of attraction between Mg plus and F minus, because here O minus, it has greater charges. If the ionic charge is greater, the lattice energy is greater. So the greater attraction between ions, the greater the magnitude of lattice energy. Second factor for lattice energy is ionic radius. Lattice energy of lithium fluoride is bigger than the sodium fluoride. This is because the size of lithium ion is smaller than sodium ion. If the size of lithium ion is smaller, the interionic distance of LIF means the distance Li is bonded to F. The distance of Li and F is smaller, it is closer. LIF distance bond is closer than the bond between NAF. Thus, the smaller the distance between the oppositely charged ion, the greater the attraction between ions. So much closer means greater attraction, the greater the magnitude of lattice energy. Electron affinity. It is the energy change when 1 mole of gaseous atoms gains 1 mole of electrons to form ion. So you have 1 mole of gaseous atom initially, 1 mole oxygen gaseous atom. It gains 1 mole of electron. It forms an ion of oxygen. O negative, it is still in gaseous state. So this is what we call electron affinity. When 1 mole gaseous atom gains 1 mole of electrons, that is electron affinity, the energy change when this gains an electron. So electron affinity is equal to negative 142 kilojoule per mole. Means the electron affinity is exothermic reaction because it is negatively charged. And for the second electron affinity means you take the second electron into that ion. So here the first electron affinity, first time, because this is the atom, not ion yet. So first time you take the electron into it, becoming this ion, an ion, and then this anion gain the electron again. So second time, second electron affinity is energy absorbed when 1 mole of gaseous ions gain 1 mole of doubly charged ion, means this is the second time. So 1 mole of an ion, O minus, plus 1 mole of electron, it gains 1 more mole of electron. This is the second time. The first time here from atoms become an ion. Second time, an ion gain 1 more mole of electron to become O2 minus. That is the second electron affinity. The second electron affinity is the endothermic reaction. Positive 844 kilojoule per mole. This is endothermic reaction. Ionization energy is the minimum energy required to remove 1 mole of electron from 1 mole of gaseous atoms or ion. So here ionization energy is remove electron. Electron affinity is accept electron. This is the opposite of electron affinity. Ionization energy, you remove 1 mole of electron from 1 mole of gaseous atom or ion. So here, if this is the first time, so first ionization energy, minimum energy required. Energy required means endothermic reaction, so it is positive sign. So this is the first time to remove electron, so from gaseous atom, Mg atom in gaseous state, remove 1 electron, remove 1 more electron, leaving 1 more of gaseous ion. So here from gaseous atom it form gaseous ion. Move 1 more of 1 electron, 1 more of electron. And then this is the second ionization energy. Initially, this is the first time, this is the second time, from 1 mole of gaseous ion. Minimum energy required to remove 1 mole of electron from 1 mole of gaseous ion from the reactant. So now your reactant is gaseous ion, so it removes 1 mole of electron from 1 mole of gaseous ion and it produces Mg2+. This is the second ionization energy. So endothermic reaction, minimum energy required, so you need that energy, so endothermic reaction. Need the energy means the energy is gained, means the energy after the reaction is bigger than the energy in the reactant. Born-Haber cycle is an enthalpy diagram used to calculate the lattice energies of ionic compounds based on Hess's law. So we use Hess's law in the Born-Haber cycle. It's an enthalpy diagram we use to calculate the lattice energy of ionic compounds. Example, construct a Born-Haber cycle for lithium fluoride. So lithium fluoride, we need to calculate the lattice energy of lithium fluoride from the following data. Construct the Born-Haber cycle for this. Now, in order to form lithium fluoride, we need the enthalpy of formation of lithium fluoride. So here these data are given: enthalpy of formation, enthalpy of atomization of lithium, enthalpy of atomization of fluorine. So if you notice, this is enthalpy of formation, so we want to form LiF. And then atomization, you atomize this one element first, and then you atomize the second element. After that, after you make it as an atom, you make it as ion. Next, you make it as ion. So for this one, Li is in group 1. So to make it ion, you remove the electron. In order to remove the electron, we do the first ionization energy. Ionization, we remove electron. And for this one, fluorine group 17. And then group 17 usually accept electron. So accept electron, it is electron affinity. So first you atomize the element and then ionize the element, and then you can calculate the lattice energy. So it's step by step. First, form the LiF and then make Li and F as the atom, and then those atoms make them as ion. Finally, we can calculate lattice energy. So those 3 steps in Born-Haber cycle, you need to follow that order. Alright, so lithium fluoride is formed from its elements in their standard states. The enthalpy change for overall reaction is the standard enthalpy of formation. So given the standard enthalpy formation, from this data, you have to construct the chemical equation. So in order to form LiF, you need Li atom, you need F atom. Here, Li exists in solid, so Li solid, you need to write down the state of matter for each element. So Li solid plus F2, but that F2 is half because you need LiF. So LiS plus half F2 gas, you will get LiF. This is enthalpy of formation. In order to form LiF, you need Li and you need F. So that's how you construct the chemical equation for enthalpy of formation. The state of matter is the state of matter that it's stable state. So Li the most stable in solid, F2 most stable in gas. So put the most stable state for reactant of enthalpy of formation, LiFS. So this is the first one. And then write down the value. This chemical equation with the value of delta H, we call it as thermochemical equation. So here delta HF of LiF equals to negative 617 kilojoule per mole. From here, you know that enthalpy of formation of LiF is exothermic reaction. Next, we have to consider the following set of steps Born-Haber cycle from LiF is formed from Li and from F2. So here, this is enthalpy of formation. We need to calculate the lattice energy of LiF. Lattice energy means from ion gas to become LiF. So the reactant must be ionic gas to become LiF. So you need to form ionic gas reactant first before you can calculate LiF. Now, first, step 1, you need to form this lithium atom from solid lithium, make it gas. Okay, make it gas first. So that is atomization of Li. Here, atomization of Li means you make this atom solid, change it to gas. This is what we call delta H atomization, standard enthalpy atomization. It is positive 161 kilojoule per mole. It's given in the question, this value. Delta H atomization for Li is 161. Here, enthalpy atomization of lithium. And then you make it gas first. This one, make it gas. That is enthalpy of atomization. Next, after you make it LIS gas, next step, you make the fluorine to gas. Atomization of fluorine, make it to gas. So write down the delta H, enthalpy of atomization fluorine, positive 79.5 kilojoule per mole. Make sure the product is 1 mole, because it's kilojoule per mole, because this delta H must be per mole. So in order for this 1/2 F2 gas to become F2, you need this enthalpy, this amount of enthalpy. So half F2 will become F gas, 1 atom only. This is atomization. You make it as 1 atom, and that atom must be in gaseous state. Next, number 3, ionization of gases lithium. The enthalpy change for this step is the first ionization energy of lithium. So you want to make this lithium gaseous atom as ion. And then you write down lithium gases to make it as ion, Li plus, gaseous state plus electron. So you remove 1 electron from this lithium atom to become lithium ion plus 1 mole of electron. Remove 1 mole of electron from here. So this is ionization energy first. First ionization energy, the value is positive 520 kilojoule per mole. Means this is endothermic reaction. You require energy to remove 1 mole of electron from lithium gas atom. Next, after you make this lithium atom as lithium ion, make this fluorine atom to fluorine ion. So to make it fluorine ion, you have to make the electron affinity of fluorine. So it gains 1 mole of electron. Fluorine atom gains 1 mole of electron to get F minus in gas. And the delta H for electron affinity equals to negative 328 kilojoule per mole. This is exothermic reaction. The value is given, it's negative, so means this first electron affinity is exothermic reaction. And after you make both as ions, formation of crystalline ionic solid from gaseous ion, then this F minus and the Li plus will be LiF solid. Li plus F minus will be LiF solid. So this is the lattice energy. You need to calculate this lattice energy and you need to construct Born-Haber cycle. Okay, before constructing the Born-Haber cycle, make sure you can distinguish between energy cycle diagram and energy level diagram. Energy cycle diagram, you don't have X or Y axis. You don't have X axis, you just put the arrow, that is the energy cycle diagram. But for energy level diagram, you have the Y axis. In energy level diagram, for positive enthalpy, because we have the mixture of positive and negative sign enthalpy, for constructing Born-Haber cycle for energy level diagram, the positive enthalpy arrow must be drawn pointing upwards, and for negative values, the arrow are drawn downwards. So this is the Born-Haber cycle for energy cycle diagram. Energy cycle diagram, you don't have y-axis or x-axis, just cycle diagram. Okay, we start with the formation of lithium fluoride. Formation of lithium fluoride. This is the equation for formation of lithium fluoride, and at the arrow you write down the enthalpy of formation value. Enthalpy formation equals to negative 617 kilojoule. So this is the enthalpy formation value. And then after we have this formation, this atom, this Li solid, make it atom gases, make it as gaseous atom. So atomization, enthalpy of atomization, Li solid, you make it as gas atom and write down the enthalpy atomization here. That's the second one. And then after that, after we make this Li as gaseous atom, you have to make this F2 as gaseous atom as well. This half F2 gaseous atom, enthalpy of atomization. So make this as gaseous atom, F gas, just one F atom and then gas. And then the enthalpy of atomization is positive 79.5 kilojoule. Write down the enthalpy of atomization. After enthalpy atomization for both, you need to do enthalpy of ionization for both. So one by one. After you atomize this, you ionize the Li. When you want to ionize the Li, this Li is group 1. So you need to do the enthalpy of ionization energy. You ionize. So ionization energy, you remove 1 mole of electron. This is enthalpy ionization energy, first ionization energy, and you put the value of the enthalpy here, and then ionize the fluorine atom. After you ionize fluorine atom, this is fluorine atom group 17, so this is electron affinity. If you want to ionize this fluorine, you call it enthalpy at electron affinity. Equals to negative 328 kilojoule. So this is the electron affinity value. And then after you've done atomize and ionize both, you can straight away calculate the lattice energy. Lattice energy, you know that lattice energy is the energy for when you have the gaseous ions convert to become solid compound. That is lattice energy. So now you have both gaseous ion and then straight away to become LiF. That is what we call lattice energy. You have to calculate the value of this. So this lattice energy here, you use Hess law. From here, from Li solid plus half F2 gas to become LiF is equal to this delta H. For this step, this delta H is equal to, you total all this, and then you can get the lattice energy here. You total all this, it is equal to negative 617. So before we calculate the lattice energy value, for this one is what we call energy cycle diagram for bond Haber. If we want to draw the energy level diagram for bond Haber, energy level has y-axis and it is labeled as enthalpy. Y-axis enthalpy, that is the difference between energy level and energy cycle. Energy cycle does not have the y-axis or x-axis, but energy level has y-axis and it is enthalpy. And mark 0, this is when the enthalpy equal to 0. We start with the formation. Always start with the formation, enthalpy of formation. So here, if you look at here, enthalpy formation, LiS plus half F2 gas to become LiFS. So you start here, reactant, write down the reactants, LiS plus half F2 gas, it will become LiFS. And if you look at this, it is negative value. If it is negative value, the arrow in the energy level diagram must pointing downwards. If you refer the previous slide, negative values arrows are drawn downwards for energy level diagram. Energy cycle doesn't matter because you just show the cycle of it, but energy level, if it is negative, this is the reactant and you want to form the product, and the arrow must be pointing downwards. So this is the product, pointing downwards because it release energy. When release energy, energy of the product will be lower than the energy of the reactant. So that's why arrow pointing downwards. And then write down the delta H formation, negative 617 kilojoule. And then this is the first one, write down enthalpy formation. After that, you have to atomize both. After formation, atomization for both, for Li and F2. Okay, we do one by one. Atomize Li first. Atomize the Li. It will become Li gas. It will become Li gas. You atomize the Li, it will become Li gas, and the value is positive. That's why the arrow is pointing upward. The arrow direction depends on the sign of the value. If it is positive, the arrow is pointing upward. If it is negative, the arrow is pointing downwards. So here arrow is pointing upward because it is positive, means endothermic. Endothermic means it gains energy, it requires energy, it accepts energy. So when this reactant accept energy, the product energy will be more than the reactant energy. That's why the product energy is higher than the reactant energy. And then now here we only focus on LIS. We only do the atomization for LIS to become Li gas. So just copy for half F2 because we didn't do anything for half F2. So just copy back whatever you have in the reactant. Okay, plus half F2. And then after we atomize Li, we want to atomize the half F2 gas. So you atomize this, and the enthalpy of atomization for F2 gas is positive, so arrow pointing upward. And then half F2, you atomize, it will become F gas. And then we didn't do anything for Li gas, so just copy back. Li gas is copy back. And then now we have atomized both Li and F. After we atomize, we need to ionize. Ionize one by one. First, we ionize Li. Ionize Li by ionization energy. Ionization energy is positive value, endothermic reaction, so arrow pointing upwards. Arrow pointing upwards, and this Li will become Li plus gas. And we didn't do anything for F, just copy back and write down the ionization energy value. Delta H3 equals plus 520 kilojoule. And then after we ionize Li, we have to ionize F. In order to ionize F, we need to do electron affinity. Electron affinity, the value is negatively charged, negative sign. The value is negative sign. So if the value is negative sign, this arrow for electron affinity must pointing downward. So pointing downward, write the value of it, and you will get the product. This electron affinity means you ionize the F. Ionize the F, it will become F minus, and you didn't do anything for Li, so just copy back Li plus gas. Here is enthalpy ionization or electron affinity, negative 328 kilojoule. Now we need to calculate the lattice energy. Lattice energy means the gaseous ions become compound solid. Means it's from here to this one. So if you look at the enthalpy for Li plus plus F minus, the level is higher than LiF solid. So the arrow must pointing downwards. Because for lattice energy, from gaseous ion to become solid compound, it is exothermic reaction. So lattice energy here, H5 is lattice energy. So the arrow is pointing downwards. And then this from Li plus half F2 gas to become LiF is equal to Li plus half F2 gas go through all this and becomes LiFs. So this is one step, and from here, from this reactant to become LiF, one step. From this reactant to become LiF, if you go through all these several steps, it's equal to the value of enthalpy formation. So enthalpy formation here is equal to H1 plus delta H2 plus delta H3 plus delta H4, and you will get the lattice energy. Just substitute all the values in there. The lattice energy will be negative 1049.5 kilojoule per mole. That is the lattice energy of LiFs. Lattice energy means gaseous ion becomes the solid compound. Thank you.